So to get started, we have the roof, and from the roof there was the spring scale that was reading the tension on the string. Then we have the string, and there's the airplane. And we know that this plane is traveling in a circular motion around a fixed point that's the center. Okay, so this spring scale reads the tension that is on this string. Reads F tension. Now we know that this plane is traveling in a constant speed around the circle. So let's first draw a force diagram for this plane. We have gravity going down. Then we have the string, the tension on the string. So if we pick this point as where the plane is, the string is going in this direction. So if I draw the string, it looks like this. This becomes my F string, or F tension. Now since this is a diagonal, it has two components. It has the upward or Y component, and it has the X component. Since this plane is only traveling in just the X plane and it's not moving up or down, we know that F grav has to be equal to the Y component of the string. So these two are congruent. So if these two cancel each other out, all we have left is this component, the X component. So basically, this here, this is our F net, or also the centripetal force. Now, speaking of F net, we have a few equations that we learned in class that pertain to F net. We know F net is equal to mass times the acceleration, and in circular motion, we found that acceleration is equal to v squared over r. We also know that F net is equal to 4 pi squared r over t squared. Now in both of these equations there are several variables. We have to find r, we have to find v, we have to find m, we have to find t. So our mass was given, we found that the mass was given to be equal to 125 grams, which is equal to 0.125 kilograms. So even though our mass is given, we still need to find or solve for the v, we need to solve for r, and we also need to solve for t. Now let's just pick one of these variables and figure out how to solve it. So we're just going to start with r, or the radius. Now in a usual problem, the radius is just the length from the center all the way to the outside of the circle. Now in this problem though, we can't exactly estimate where the center is, nor can we find where the end of the circle is because it's traveling in the air. So how do we find the radius?
Many times, architects build smaller versions of their actual buildings, and these are called scale models. Now, the ratio of the measurements of the scale model over the measurements in real life in the actual building, this ratio is always consistent throughout the whole model, and this is called a scale. So, our group took this idea of a scale model and applied it to this airplane lab. So first, our group member took a picture of the plane while it was in motion. And this is what the image looks like. So I just retraced the string here and tried to draw 90 degrees
going down. And so what we're doing is we're finding the measurement of the image and putting it over the measurement in real life, and we're creating a proportion. So what I mean by this is, for example, if we measure the length of the string in this image in centimeters, it's approximately 4.5 centimeters long. Now, so that's the measurement in the image, 4.5. Now, if we look at the actual plane, we can measure the string by figuring out when the plane stops moving, and it's just, the string is exactly just going down with the plane at the end. We found and we measured the length of this string, and this was equal to 75 centimeters. So this was in real life, the length of the string is 75. So we put the 4.5 that we measured on this picture over what we measured in real life, which was 75 centimeters. Now we can continue this proportion by figuring out the radius in this picture. Now, assuming this is the center, we're trying to find the distance between the center of the circle to the outside. So if we measure this, we find that it's a little bit less than 4. So we're going to put 4.5 centimeters over 75 centimeters is equal to 4 centimeters over, so this is the radius in the image, so this proportion, the radius in the image, so the 4 centimeters that we measured in this image, we put that over x, which is going to be the radius in real life. So we just created a simple proportion. Now we could use cross multiplication to find that 4.5 centimeters times x is equal to 4 times 75. And when we plug it into the calculator, we could solve for x to be 66.66666 and round that to 66.67 centimeters. This is the radius of our circle. To find the velocity, we know that velocity is equal to delta x over delta t. Now, x is the distance traveled. If something's traveling in the circle, delta x is actually the circumference of the circle. The plane is traveling on the outside of the circle. So the equation for the circumference is 2 pi r, which is also equal to pi d, over the time that it takes to travel that. To find the circumference of the circle, we already solved for r. If you remember, r we found was 66.67. Now all we need to find is the t. Now to find t, it's basically just doing many different trials and finding the average. So we want to find t, if you look at this image, is how long does it take for this plane to go around the circumference of the circle and return to where it started. Now sometimes this can be a little too fast to record on your phone to measure the exact time. So what you can do is start your timer, let the plane go around a few times. So our group, we found the time it takes for the plane to go around 4 times. And after this 4 times, we had a number, and we divided that by 4. And when you divide it by 4, you find the time that it takes for the circle to complete exactly 1 circle. So we did many different trials, and we finally found the time to be 1.1228 seconds. Of course, there will be some error in this number, as we used an iPhone stopwatch to record the time. So now we have the circumference of the circle over the time. Now we can use our calculator and plug in those numbers. So What we want to remember here is 66.67 is in centimeters. And when we're finding velocity, we're finding meters per second. So when you put it into a calculator, it has to be 2 pi times 0.6667 divided by the time, which is 1.1228. To find the velocity is 3.73 meters per second. This is our velocity, and this is our time. So going back, we can check off velocity and time. All we need to do now is use this equation and plug everything in. Now we just need to throw everything into our Fnet equation. Now we can check it both ways since we know two different equations. So first we're going to use the mass times the acceleration for r. So we found the mass, which was given 1.25 kilograms, times the velocity, which we just solved for, 3.73, square it, over the radius, which we solved for, was 66.67 centimeters, which is 0.6667 meters. Now throw this all into the calculator. We can have 0.125 times 3.73 squared divided by the radius, 0.6667. And we found Fnet equals 2.6. Good. Now we could check this with our second equation, which is Fnet equals 4 pi squared r over t squared times the mass. So now we just need to plug in everything, the radius, 0.6667, mass, and the t. Get all into the calculator to get 2.60. Yay, we found Fnet, so we finished this lab, right? Nope. Let's return back to our original notes to see what the objective of this lab was. What we were trying to do was find the reading on this spring scale. Now, we know that the spring scale reads F tension. What we just found was Fnet. So going back to our force diagram, we have gravity. We also know F string or tension. We have these two vectors that are equal. And then we have this, which is our Fnet, or also the x component of the F string. So this is Fnet. So this number we just found, 2.6, that is equal to this component. So that's 2.6. What we're trying to find is this F string or F tension. So let's start with gravity. How do we find the gravitational force on this plane? We know gravity is equal to 9.8 times the mass. 8 times the mass. So that's 9.8 times 0.125, which is equal to 1.225. So we know the F grav is equal to 1.225 newtons. Now we have these two congruent symbols, which means that this is equal to this. So since we know that this is 1.225, we know this is also 1.225 newtons. Now we know this and we know this, which is the same as this since they're just the same line. So 1.225. So now what we have here is a right triangle that we can solve. We know that if this is A and B and C, we know that Pythagorean theorem, a squared plus b squared equals c squared. Now we can plug in the numbers, so 1.225 squared plus 2.6 squared is equal to c squared. Now, if we actually plug this into a calculator, we know that c is equal to the square root of 1.225 squared plus 2.6 squared. I'll write that down. C is equal to the square root of 1.225 squared plus 2.6 squared. So that's easier to plug into our calculator. Square root of 1.225 squared plus 2.6 squared equals 2.87. So we found C, which is F string or F tension. F tension on string is equal to 2.87. 2.87, almost 2.9. The F tension is what is read on this spring scale. So we just solved for F, the tension of the string, and we got 2.89. That's our prediction. Good job. Now, if we look at the actual answer, Mr. Bushka actually stood on a chair and read the spring scale. It was about 3. And our prediction was 2.87, about 2.9. So we were really close. Now, can you think of some possible errors that we could have, or possible reasons why our number was lower than the actual number?